We have a polynomial question tonight, folks. I'm going to go ahead and stipulate. We probably could get away with this, but it will give us a sense of the reasonableness of our answer. I'm going to go ahead and say that it has degree n. Okay, degree is equal to n, and that means just the highest power present as an exponent of n. Okay. Now this particular polynomial, and also I don't think it's important whether we stipulate if it has real or complex coefficients. We can say real if you want, but it probably could. Nothing we do here would be violated by having complex coefficients, I think. Now what we've given is quite a bit of information. Hopefully it's readable. If a polynomial p of x has remainders 7 and 13 when divided by the linear factors x minus 3 and x minus 4 respectively, we want to find the remainder when p of x is divided by x minus 3 times x minus 4. Now notice this new divisor will have degree equal to 2, right? X squared is the highest power, right? So the degree of this is equal to 2, which means the remainders could either be constant or linear. That is degree 0, degree 1. Remember, any constant, for example, any constant c can be written as c x to the 0. So this constant is sometimes called degree 0 itself, okay, the degree 0. And again, a lot of this may not be worth the time, but the constant is degree 0 for this reason. Okay, now let's move along. Now, what we're looking for, just by the division algorithm, we're seeking a remainder r in this form. And notice we wouldn't expect r to necessarily be a constant here, since the degree of this, as we mentioned, is degree 2, and so possible remainders would have degree 0 or degree 1. Okay, so in other words, we don't think that r is necessarily just a scalar or a real value. Okay, now this is nothing more than a statement of right here we have a remainder of 7 upon division by x minus 3, and we'll call q1 of x our quotient. Okay, so we would here q1 would necessarily have a quotient of n minus a degree of n minus 1. Maybe not so important to mention that. Okay, now we can play the same game with q of 1, the quotient in the previous problem, and then we utilize the x minus 4 factor here. And you can kind of see the motivation for this. Now, notice r, again, like I said, it doesn't necessarily have to be a constant based on what we've said earlier. So doing the substitution, we're going to do a substitution right here. And notice that p of x is equal to this, q of 1 is equal to this. So we literally place this right here on the very next line. That's what the substitution was. We substituted this expression into exactly right here, okay? And we get this. Now when you distribute this out, you distribute the x minus 3 over both things. And you see the nice thing about doing this is we get something that's close to what we're looking for. We have q of x, some q of x, times x minus 3 times x minus 4, and the r is sitting there, right? So as that's what we're already getting something that kind of smells like this expression right here. All right. Now, what piece of information haven't we used? We also know that p evaluated at 13, or p evaluated at 4 would be 13. Let me write that down. P evaluated at 4 and this is just the remainder theorem at work here. P evaluated at 4 is equal to 13, and that's given. Okay, P evaluated at 4 is equal to 13, and again, why? When you divide P of x by x minus 4, you do get a remainder of 13. All right, and so when you substitute the 4 in, the quotient will go away, and you're just left with a constant term 13. All right, like for example, right here, P at 3 would be 7, right? I didn't write down an explicit statement here, but P at 3 would be equal to 7, and in a similar fashion, P at 4 is equal to 13. Okay, so what do we get right here, though? That would mean, and again, this is just a statement of truth right here. So, see this piece right here, if you substitute 3 in right here, or if you substitute 4 in right here, this part just would become 0, right? So you would have 0 plus r right here. And I'll make this complete in just a minute, folks. 0. 4 right here gives you 0. The rest of it all is 0, right? So you would get 0 plus r times, let's see here, or this is plus, excuse me, that would be plus. Okay, we'll have 0 plus r plus. Okay, we're trying to figure out what 4 is, or what r is, right? So we have r right there, and then 4 minus 3, right? 4 minus 3, let me just write it for emphasis. 4 minus 3 plus 7, right? Now remember, this is all equal to p at 4. Which is equal to 13. And that's given information. Again, folks, this follows from something called the remainder theorem. All right, and so what do we end up with here, ladies and gentlemen? We end up with r. 4 minus 3 is 1, so we have r plus 7 equals to 13. And you see, what does that imply? That implies that r is equal to 6. Okay, folks, that means that r is equal to 6. And so what we can do right here, folks, again, we'll go back up here and look at what we have. This would end up being p of x. Again, I'm just filling in the numbers. Okay, so here's our p of x, and we figured out what r is right here. So we can write down p of x is equal to q of x, and again, this is the form we were seeking at the beginning of the problem. Q of x times x minus 3 times x minus 4. And y'all, just to make sure we're clear here, I'm exactly here. I'm just recopying this statement right here, okay? But now we know, I'm sorry, I'm right here. I'm copying this statement right here. But we already know what's going on right here. R is equal to 6, right? So this would be plus 6 times x minus 3 plus 7, right? Okay, so we're just about there. So notice, folks, and I'll just write it out. This part right here would just be 6x minus 18 plus 7, which would be 6x minus 11. Okay, so this would be our remainder, right? This would be our remainder because we have it in the form we were looking for, all right? And let's see where we go. All the way back up here. Again, we were looking for something like this, x minus 3 times x minus 4 times quotient plus a remainder, and we got it in that form by just some not too difficult manipulations. So the answer here would be r is equal to 6x minus 11. And notice this is degree 1, which is consistent with you know, the properties of degrees and remainders and all that, right? This is degree 1. Degree equals 1. Could have been degrees equal to 0, possibly, you know, but it turned out to be degree equal 1. So that is it, folks. And so again, the basic structure is just 2 applications of the division algorithm, and then at that point you utilize the fact that p at 4 is equal to 13. P at 4 is equal to 13. So that does it. That's the end of the video. Thanks for viewing.